Hey, in this lecture we're going to study the topic of center of mass. This is a second part to the study of momentum, and we will shortly see how center of mass of a system is important to determining what the momentum of the system would be. Now, I have mentioned the word system very loosely. We have not yet given a very specific definition of what we mean by a system. In this chapter, let's go ahead and say very formally that system is nothing but a collection of many different particles or objects. So why is it important to us that we define a system? Well, to define what center of mass is, we have to know that system may consist of multiple particles or multiple objects, and then center of mass of a system is a point in a system through which all of the mass of the whole system appears to act. Alright? In another sense, you can think of center of mass being the point of balance. So if you ever tried to balance a ruler or something straight on your fingers, which I tried and failed because I couldn't balance it, you could only balance this thing at a very specific point. That point would be the center of mass. As you can see, I am repeatedly failing to balance it on my fingers, so I will not try again. More formally though, back to physics, definition wise, we define center of mass to be a set of coordinates, a x position or an x coordinate and a y position or a y coordinate. The x coordinate is found by this formula, which reads m total, so the mass of the total system, the combined system, times xcm. Xcm means the center of mass x position, equal to the summation over I of the product of mi times xi. Now I denotes the ith object in the system. So I equals 1 means the first object, I equals 2 means the second object, and so on and so forth. So each individual mass, m1 is the mass of the first particle, m2 is the mass of the second particle, and so on and so forth, multiplied by its individual position. So m1 times x1 would give me the mass times the coordinate for the first particle. m2 times x2 will give me the mass of the second particle times the position, x position of the second particle, and so on and so forth. Similarly, we define the y position to be m total times y center of mass equal to summation over I of the product of mi times yi. So the mass of the ith particle times its y position or y coordinate. So if we are trying to determine where the center of mass of a system is, our goal would be to find xcm and ycm from these set of formulas. Now, the only best way we know so far to understand a topic completely is by going over an example. Let's go ahead and do that. In this example, we are given this H2O molecule, the water molecule, and as we know, if we have ever taken a course in chemistry, that the water molecule is arranged in a very specific manner, making an angle of 104.5 between the two hydrogen atoms between one oxygen atom. And the distance of separation from oxygen to hydrogen for each of these hydrogens is roughly 96 times 10 to the minus 12 meters, which is very, 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 very tiny. Now we want to find the center of mass of this system, the system of this collection of molecules. So the system would be the combination of H2O, water as a whole. The particles in that system separately are oxygen, hydrogen, hydrogen. So in this way you can sort of identify the difference between a system and each of its particles. We want to find the center of mass location of this whole system. Given also that the mass of oxygen is 16 times the mass of hydrogen. So anything that's going with O is for oxygen, anything that's going with H is for hydrogen. Alright, let's go ahead and do that. First of all, since it's a physics problem and we are dealing with coordinates, let's draw out a rough coordinate system. At the center of this coordinate system, which is the origin 0, 0, both x and y coordinates are 0, we have oxygen. Okay, here lies oxygen, and from here, this is the y-axis, this is the x-axis, and from this oxygen we will have the hydrogens at two ends of a triangle. Here lies one hydrogen, here lies another hydrogen. Okay, and the angle between them is given to me as 104.5 degrees. That's all I know. Now remember that our definition was to find x coordinate of the center of mass. We have to find out each of the x coordinates of each of the particles in a system. How many particles are there in the system? 3 particles: oxygen, hydrogen, hydrogen. So our first job would be to find the x coordinates of all these different atoms in the system. Alright, so let's go ahead and do that. So what is the x coordinate for oxygen? Well, it is, oxygen is at the origin, so m, actually not m, x0 is the position for oxygen, O, xo actually. xo is 0 because it is right here in the origin. But what is xh? Well, they lie somewhere over this x coordinate, whatever this x coordinate may be. Both of them actually, if my drawing is accurate enough, they lie directly above and below each other, so their x coordinates would be the same. Alright, so now we see that it is forming a triangle. Our job to make our lives easier would be to make it into a right angle triangle, alright, because that's how we do things. So let's make it into a right angle triangle, in that this angle is being equally bisected through with this line. So now we have this right angle triangle. Right, this right angle triangle, this forms a right angle. So if this angle is bisected through the middle, then these angles are equally separated out, as I think it's 54.5. It's actually 52.5 degrees, and this is 52.5 degrees. Now let us use these two triangles to find x positions of both of the hydrogens. Now, using this upper triangle, we can see that if we already know this side of this hypotenuse. We know this hypotenuse has length of 96 times 10 to the minus 12 meters. So since we know one of the angles, we can find this side. So let's call this x1, and let's call this x, actually that's not x, sorry. Let's call this x1, and let's call this x2. Now remember that h here is exactly above h here, so both of them will have the same x coordinate. So x1 will actually be equal to x2, and let's call this, both of these, xh to denote the x coordinate for hydrogen. Alright, so from that triangle, because this is the opposite side of a triangle and this is the adjacent, so the x coordinate will be found by cosines. So cosine of 52.5 degrees is equal to adjacent over hypotenuse, which is 96 times 10 to the minus 12. x1 is equal to 96 times 10 to the minus 12 times cosine 52.5 degrees. This comes out to be 58.8 times 10 to the minus 12 meters. Therefore, the x coordinate for both of these hydrogen, xh, is equal to 58.8 times 10 to the minus 12 meters. Okay. Now, what about, we have found out both of these x coordinates. Now let's do that for the y coordinate. Since this side is also 96 times 10 to the minus 12, and this side is just in the positive y-axis, this side is just in the negative y-axis. Let's call this y1, let's call this y2. y1 is actually equal to y, well, same thing, y2 is actually equal to y1, all right, because they would be the same length, so we have to calculate it only once. So this is the opposite of this triangle, so we can use signs. So y2 and y2 and y1 is equal to the hypotenuse 96 times 10 to the minus 12 times sine of the angle 52.5 degrees. Then y1 is just equal to 75.9 times 10 to the minus 12 meters. y2 is just negative of y1, which is negative 75.9 times 10 to the minus 12 meters. Now we have all the coordinates for to calculate our center of mass. Also here we can notice that y0, the y position for the oxygen, is also 0 since it's at the origin. So we have all that we need to use our formulas. Remember what our definition was. It was the total mass times x position of the center of mass equal to the summation of each of the separate masses times their separate coordinates, x coordinate in fact, for the x center of mass position. Now what is the total mass of the system? The system consists of 2 hydrogen, so H plus 1 oxygen. So it has mass contribution by 2 hydrogens and 1 from oxygen. So the total mass would be mass of the oxygen, MO, plus 2 times mass of the hydrogens times the x center of mass position. This is equal to the summation of individual mass times their individual coordinates, meaning we have M0, the MO, which is the mass of oxygen, times x position of oxygen, XO, plus M1, 1 belongs to this upper hydrogen, let's call this 1 here, and 2 belongs to this lower hydrogen, M1 X1 plus M2 X2. All right, that is all that is in this equation. Now remember what M0 was. MO or M0, whatever you want to call it, is 16 times mass of the hydrogen. So 16 mass hydrogen plus 2 mass hydrogen would be 18 times mass of the hydrogen times the x center of mass position. This is equal to, now our coordinates come into play. Remember, x0 equals 0, y0 equals 0. So since x0 is 0, this term goes to 0. M1 is the mass of this hydrogen, so let's replace it by MH. X1 is what we found here, times 58.8 times 10 to the minus 12 meters, plus M2 X2. M2 is also the mass of hydrogen, so same thing, MH. X2 was, remember, equal to X1, so X2 is also the same, 58.8 times 10 to the minus 12, and we want to solve for this. So divide both sides of the equation by 18 mH. So you have separated out x center of mass position, and then mH is on all of these terms, so mH will go away. So you don't actually need the numeric mass of hydrogen, although we know it's pretty simple. And then we just add these two numbers and divide them by 18. So they're the same numbers, so adding them would just mean multiplying them by 2. So we have 58.8 times 10 to the minus 12 multiplied by 2 over 18. This is the x center of mass position, and that comes out to be 6.53 times 10 to the minus 12 meters. This is the x center of mass position. Now let's go ahead and find the y center of mass position. For the y center of mass position, we have the similar kind of formula that we had for x center of mass position. We just replace x's with y's, right? So the total mass is still 18 times the mass of hydrogen times the y center of mass position equal to the summation of the separate masses and their y coordinates. So MO, the mass of oxygen, times the y coordinate of oxygen, plus M1 times the y coordinate of the top hydrogen, plus M2 times the y coordinate of the bottom hydrogen. So again, y0 is also 0, or y0 actually. This goes to 0. M1, y1, M1 is mH. So 18 mH times ycm is equal to mH times y1. y1 is what we found to be here, 75.9 times 10 to the minus 12, 75.9, plus m2 is again mH, but y2 is negative y1. So it is negative 75.9 times 10 to the minus 12. They are the same number but of opposite signs. So when we add, this side goes to 0, meaning the y position of the center of mass is at 0 meters. Alright, so total, the center of mass position is xcm comma ycm. This gives me 6.53 times 10 to the minus 12 meter in the x direction, that's the x coordinate, and 0 meters in the y direction. That is how we find the center of mass of a system of particles like this. Okay, so now we have seen that how we can calculate center of masses. But why do we care about such an obscure thing? It is not obscure, as it turns out, because it makes our lives, or our physics lives, easier, since we can simplify our problems to just systems and not worry about individual particles in the system. So for example, for the center of mass, you can consider the total system together and consider the momentum of the total system, and that the total system momentum is equal to the summation of all the different momentums of all the particles involved. For example, if you have a box and the box is, say, moving with some velocity, and this has a mass, say m total or capital M, this will have a momentum which is equal to the total mass times the velocity of this box. Now this box is a system, but however we have to remember this box is made up of millions and millions of millions and millions of tiny particles. It is obviously easier to consider this whole system together and say momentum is the total mass of this box times its overall velocity of moving in the rightward direction, than taking each of these separate particles and then summing all their separate momenta together. We can only do this because of the idea of center of mass, because the velocity of the center of mass, as it turns out, is the direction of each of these particles in the system. Alright, so the momentum of the center of mass of this box is equal to the momentum of each of these particles inside that box system. So it often makes our life easier when trying to deal with momentum problems. Another reason would be to look at the net force on a system. So take that same box, for example, the net force on this box, alright, if it's accelerating, we can say in the rightward direction, we can say that there is a net force in the rightward direction as well, right? But again, there are millions and millions of particles that makes up this box. So if we didn't have the concept of center of mass, that the velocity of the center of mass is the same as all of the velocities that make up the box system, it is also the acceleration of the center of mass is the same as all the individual accelerations produced by this net force on all of these particles forming that box system. So when we have the center of mass acceleration, we can just multiply it with the total mass of the box to get our net force on the system, rather than going individually to each of these particles and calculating the net force on all of them. All right. So what this does, about what center of mass does, is actually make our life a lot easier, just because of the fact that the center of mass, whichever way it is moving, it just means that the whole system is moving with the center of mass. So simplifying a lot of our problems in the process. Now let's look at another example which gives me a different set of idea on center of mass. Let's examine a bagel. Maybe you like bagel, maybe you don't, then you're like me. But however, this is very useful in testing an idea about center of mass. Where do you think is the center of mass of this bagel? Well, if the mass of all of these dough that makes up this bagel is uniformly distributed all over the bagel, which it is in most cases, then the center of mass turns out to be right at the center. However, as we know, if you have ever seen a bagel or a donut, that center is a hole. So the center of mass is not physically inside the object you're considering. So the center of mass, therefore, can be outside the system as well. So I hope this center of mass idea makes some sense.